This problem is a relatively long description, and we start with the idea that you have a flask with a solution of calcium nitrate, silver nitrate, and chromium-3 nitrate. To this we're going to add some reagents and get some precipitates and separate solutions in order to separate these three materials. Now we can start with the idea that from Solubility Rule 2, all nitrates are soluble. So that means we're really dealing with the cations in solution that we might be interested in separating. So in our first solution we're going to have calcium cation, and I hope you know that it's in column 2, so it's 2+. We have silver nitrate, so that would be the typical oxidation state of silver, which is +1. And we have chromium-3 nitrate. Okay, so that tells us the charge is 3+. Now, to this solution we're going to add potassium bromide solution. Okay, so that means we add K+ and Br-, right? Potassium bromide. Well, obviously potassium isn't going to do anything, so what we're really concerned about is the bromide. Now, hopefully you remember that there is a solubility rule that is Rule 3 that says that all chlorides, bromides, and iodides, and we'll focus on bromides, all bromides are soluble, but there are some exceptions, and one of the exceptions is silver 1+. So, we have found a way to take silver 1+ out of our solution, because calcium 2+ does not precipitate with bromide, and neither does chromium 3+, according to the rules. So, we know now that our solid here, for the first one, where we say we add potassium bromide and we get a pale yellow solid, our yellow solid must be the result of silver plus and Br- precipitating. So that must be, since silver is 1+ and Br is 1-, this material right here. Alright, so this is our precipitate, and I can write the net precipitation reaction on the next page. So that would be silver plus in aqueous solution plus Br- in aqueous solution makes a silver bromide solid, and that is our first yellow precipitate. Now, let's think about what stayed in solution. If silver bromide precipitated out, that means we're still going to have calcium 2+ and chromium 3+ that are in solution. And our next material that we're going to add is potassium sulfate. Okay, so that means we're going to add K+ and SO4 2- ions. Okay, once again, we're not really worried about the K+ because it's typically soluble, so we're concerned about this sulfate. Okay, and what might happen when it encounters calcium 2+ or Cr3+. Now, there is a solubility rule 4 that says all sulfates are soluble, but again there is an except. Okay, and one of the exceptions in that rule is calcium 2+. So we know that calcium 2+ is going to precipitate with sulfate 2-. So this time I will just write the solid for you. calcium is 2 plus, sulfate is 2 minus. So our precipitate is CaSO4, and that will be our solid. And when we write the net equation, this means Ca2 plus in aqueous solution meets sulfate aqueous to make this a solid right here. Okay, now we only have one material left in solution since we've isolated the calcium sulfate solid by filtration. We now just have Cr3+. So what happens here? We have Cr3+ floating around in solution, and this time we're going to add potassium sulfide. Okay, so that means I have K+ available and S2- available. So once again, cation meets anion. Now, as far as the material that we're going to make, remember that chromium is going to be a +3 and sulfur is going to be a -2. So in order to balance the charges, we need 2 chromiums and 3 sulfurs. That will be our solid, and it tells us that this is a brown precipitate. Okay, and if I write the net balanced reaction, I have chromium 3+ aqueous and sulfur 2- aqueous meeting to make this solid, but remember to always balance. So there should be 2 of the chromium 3+ and 3 of the sulfide 2-.